Hello, hello. Hi, everyone. Welcome to our first day of class. We're gonna jump right into it with our Unit 0 page and then our Unit 1 page. So this is gonna be from the modules. So hopefully you watched the introduction video so you know where these actually are. Okay, so please keep that in mind. Let's go ahead and just get started. So we're gonna review some tidbits of Cal 1. We're obviously not gonna review all of Cal 1. We're gonna try to hit a lot of the bullet points. So first, let's just go over exponent notation. Um, when we have two items that are multiplying and they are the same base with two different exponents, we can shortcut it by saying that it's that base, but to the power of the sum of those two exponents. So if I have a to the power of m times a to the power of n, I can just write it as a to the power of m plus n. For over here, it's a similar vibe, but you say a to the power of m minus n for division. The gimmick for subtracting is we have to remember that when a power is negative, it implies that it's in the bottom. So you can technically take a beat and rewrite this as a to the power of m times 1 over an. But then you should know that with this idea, you can write as a to the power of m times a to the power of negative n. And then you add these two guys to get a to the power of m plus a negative n, but we all know that is just this. Similar idea, if there's a negative in the bottom, that you can just bring brought up to the top. A double negative makes it positive. And then if we're multiplying, or not multiplying, excuse me, if we have a power of something that has a power on it, then we could just rewrite it as a product. We multiply those two powers together. Similar here, they kind of both distribute a to the power of n over b to the power of n for any fraction. And then for any number 0, we know that that's supposed to be 1. Square roots, they're commonly referred to as x to the power of 1 over 2, or we can rewrite here as the x to the power of negative 1 over 2. Ultimately, if we're left with an nth root, we can attempt to rewrite that as x to the power of 1 over n. So pretty straightforward, just review stuff. I'm not going to reteach it from the ground up. If this confuses or like ask questions, just let me know. I could definitely make a video about it, no big deal, but yeah. Okay. All right. Next we have limits and derivatives. So this is just, bullet points basically. Let's start with this idea. If we have some power, x to the power of n going towards infinity, then that's going to be infinity itself. If we're taking the limit as x goes to infinity, x to the n, then that n should be negative. So that means that you could technically argue that we're actually taking the limit as x goes to infinity for 1 over x to the n. And then that way x is positive. So it's kind of the similar thing, but it's just, different coats of paint on how to do it. Here we know exponential and logs as they go towards infinity, they keep increasing, so that's why those limits are also infinity. Same thing for the square root as well. It technically falls into this category. And we know for trig functions, there's not a limit as it goes to infinity because they keep squiggling or they keep like repeating waves and things like that. If a degree of the numerator is less than the degree of denominator, the function is bottom heavy and the limit is 0. If degree of numerator is equal to degree of denominator, the function is balanced and the limit at infinity is the ratio of the leading coefficients. If degree of numerator is greater than degree of denominator, then it's top heavy and limit at infinity is either plus or minus infinity. I believe that's a typo. And then L'Hopital's rule, if you have when you're taking limit using substitution, if you have 0 over 0 or infinity over infinity, then you could take the derivative of both the top and the bottom, and it should be the same thing. Derivatives. Constant can escape. If you're doing the sum or subtraction derivatives, you could just apply derivatives to the functions each. If it's a constant, it's 0. This is power rule. You bring the power down and you say n minus 1 to that power. If you're doing this is product rule. You do f of x times g of x, you do the derivative of f times a regular g, and then you add it to derivative g times f. Quotient rule has a similar vibe. The only difference is that you're subtracting and it's dividing by that bottom part squared. Okay. Then this is chain rule. If you have a function within a function, you're taking derivative of it. You technically do derivative of the outermost function with the remaining function inside intact, and you multiply that by the inside's derivative. Over here, if you have y, where y is a function of x, then while you take the derivative, you're technically multiplying it by the derivative itself. Similar ideas for sine, cosine, tangent, secant, and then the secant inverse, cosine inverse, tangent inverse, exponential, log, or no, exponential, and then exponential with an alternate base, and then logs as well. Okay, let's do some quick limits. So here we see that 2 is better than, or 2 is not better, 2 is greater than 1, and it's in the bottom, so that means it's going to be bottom heavy. It's going to be 0 as our limit. For here, we see that those two are balanced, they're both 3. So that means it's just going to be a ratio of the coefficients with 1 over 2. Here, similar vibe, 5 over 2. Here we have negative infinity, so we see that it's top heavy. But then we ask ourselves, okay, well, if it's top heavy, you know, that means we're going towards infinity. But what's negative infinity? Or what's a negative number cubed? Well, that's going to stay negative. So it will go towards negative infinity. Let's take a beat and let's acknowledge that both of these, if we did the limit by just plugging in, we get an infinity over an infinity situation. We can use L'Hopital's rule. L'Hopital's rule states that we could take a derivative. So we take a derivative, we get negative, what is that? 12x to the power of 3 plus 2x over 2x. The constants disappear. Okay, you could technically split up these fractions and you'll see that the answer would be infinity, or negative infinity, excuse me. But let's again just acknowledge it's infinity over infinity, so you use Hopital's rule again, so you get negative 12x to the power of, or no, excuse me. I'm going too fast. Let me see how many. Oh yeah, I'm going a little fast. Okay, I'm trying to slow down. Negative 36x squared plus 2 over 2. And then you could, like, kind of how I said it here, you could split these up, but for here, you just would plug it in, and you see the top part go towards negative infinity, so that limit is negative infinity. You're not dealing with an infinity divided by infinity anymore because the bottom part is just 2. Similarly, over here, if we wanted to take the derivatives and we keep going, we could, and we would get probably a negative number on the top with some guy on the bottom, probably be a 6. So this is also just going to be negative infinity. Okay. All right. Antiderivatives. An antiderivative of a function. An antiderivative of f of x is a function capital F of x such that f prime of x is equal to f. Warning, antiderivatives are not unique. If capital F is an antiderivative of f of x, then capital F of x plus c, where c is any constant, can be positive, negative, or 0, is called a constant of integration. So for example, if I do derivative here, I get 3x squared. If I do derivative here, I get 3x squared plus 0. If I do derivative here, I get 3x squared plus 0. Because derivative of constant is 0. These are all technically the same answer. So if you had to go backwards, you start off with 3x squared. You really have no choice about going here, here, here. So in order to leave it into proper interpretation for any of these constants, you would say x cubed and then plus a c to make room for any one of these possible constants. The way we do antiderivatives is technically an indefinite integral. So that means it's just the general formatting of it. Recall the power rules. This is the forward, this is the backward, and don't forget for most integration, it is just you going backwards from the derivative. So let's really dive into it with a good just worksheet style review. If I take the derivative of all these, right here we got a power rule. That's going to be 12x. Right here, it's kind of a power rule, not really, but you just get rid of the x, -4. Here it's trig, so we go from negative sign to cosine, negative cosine, excuse me. And here we get a 0. Um, let's go backwards. Well, here we see that that's just power rule, so 12 to multiplying x to 1 plus 1, so 2 over 1 plus 1, 2. -4 times, let's say there's x is 0, then that's going to be x to the power of 0 plus 1, which is just 1, over 0 plus 1, which is just 1. And then going from negative cosine, that's going to be sine of x. And then plus c, because we don't know if there was a constant that could have been there. In this case, there was, but still. It doesn't look exactly like it though. We need to do some simplifying. That's going to be 6x squared. That's just going to be -4. Dividing by 1 doesn't do anything. X. And then negative sine of x plus c. So again, notice how these guys are opposites of each other. You do a derivative to get the integral part. You do the integral part to get the derivative. It's gonna happen to you guys where we're gonna be focusing more on integrals, and out of habit, especially if you're just coming off Power 1 in the summer, you're gonna fall for that trap of making everything a derivative when it's supposed to be an integral. Alright, let's keep it going. Over here, we got 3ex. We know ex, derivative is just ex. Tangent is secant squared of x. And over here we got -6x and then a 0. Over here it's the same thing. We get 3ex. The derivative, or not derivative, the function that derivative is a secant squared is tangent. And over here we could do a little bit of power. We got 6x to the power of 2 over 2, because that's 1 plus 1. Let me quickly say that. I'm thinking maybe a little too in review. So remember, antiderivative says if we have a power of x to the power of n, we simply write it as x to the power of n plus 1 divided by that n plus 1. So that's why I keep saying 1. I keep saying 1 plus 1, or like the plus 1 idea over here as well. We're not done here, although we're very close to being done. We just simplify that to be -3x squared, which again matches. Over here, I'm going to take a beat and rewrite this as a power. So I know that's 1/2 and then -1/2, or -1/2 minus 1, which is negative, or I said that wrong, I think. Let me rewrite it. Or here, I'm writing like this. I take 1/2 in the front, x to the power of 1/2 minus 1. And we know that is equal to negative -1. And that can be written as this. Similar-ish vibes, but you have to look at it just differently with that power rule idea. So you would just rewrite this as 1/2 x to the power of -1/2, and then you add 1. So let me just do that a bit visually. -1/2 plus 1 over -1/2 plus 1. 1/2 x to the power of 1/2 over -1 plus 1, 1/2. Those 1/2s will cancel out, and you're just left with x to the power of 1/2, and that's square root of x. Over here, similar vibes are going on. For x to the power of -3, we know that, excuse me, we know that's just jarring the power to -12 x to the power of -4, and then we rewrite that as -12 over x to the power of 4. Over here, you can do it, oh, sorry, you could do a similar rewriting trick. You get -12 x to the power of -4, and then you're going to go ahead and do that power rule that we mentioned. X to the power of -4 plus 1 over -4 plus 1. These are both going to be -3s. That can simplify into a +4. And then we can just rewrite it as 1 power. Oh, I forgot a step for both here and here. And here as well. What did I forget? The plus c. Remember, we have to leave room for the possibility of a constant being hidden within. We could see that there's not a constant because we have the left side to compare, but that doesn't mean that there can't be a constant. So keep that in mind, pretty please. All right. Last one. We have 2 over x minus sine of x and then plus 0. And then here, that's going to be 2 ln of x going from negative sine, that's going to be positive cosine, and then plus c. Okay. So pretty straightforward ideas here. The only things is that I'm like kind of worried about for these videos is that, wait, what the heck? Did I do that? I don't even know how I did that. Did I move the lesson today? I guess I did. I don't know when I did that. Um, the only thing I'm worried about, oh, you guys watching these videos, is that you gotta make sure that you really review Cal 1 material, or you at least know like how to ask for it. I don't know, it's a bit tricky because this is online, right? So just have any questions, please do not hesitate to reach out, okay? I feel like I'm very responsive, like I have the apps on my phone, not on my phone devices. So just please keep that in mind. Okay. All right. It's gonna be it of the review packets. Let's go ahead and do the first two sections of the Unit 1 packets. So integration. So we'll be using rectangles to approximate the area underneath the function. This is the foundation, what we now will call integration. Oh, I copied and pasted this, sorry. To approximate the area under F from A to B using n rectangles. So we have the segment A to B, and we divide the segment into n subintervals of equal width, defined here. We pick a sample point xi in each subinterval. These can either be the left or right endpoints. So if we pick the left, they'll look like this, and we pick the right, they'll look like this. Compute the height of the rectangle by plugging the sample point into the function. The area of the rectangle is height times width. So the height would be f of that x that we plugged in. And then the width would be that width we mentioned earlier. And then we add all the areas. So again, left endpoint right here, we have this little gaps in between. Right endpoints, we have this overlap. So traditionally, although you can see examples, sometimes a left endpoint will underestimate while a right endpoint will overestimate. And ideally, the closer we get with these ends, the more true we'll see into the actual area under the curve. So the higher the ends, the closer area we'll see. But let's go ahead and just do this example. The example reads, estimate the area under f of x is equal to 2x squared minus x on the interval 1 to 3, using 4 rectangles and left endpoints. Then compare that to the area using right endpoints. Well, first off, we need to find the width. The width will be the same for both the left endpoint example and the right endpoint example. Well, they want us to look from 3 to 1, or from 1 to 3. But we need to organize it in 3 to 1 like so. And then they said 4 rectangles. That's going to be 2 over 4, or just 0.5. So let's go ahead and go over here. When we have I is equal to 1, we'll have x0 is equal to a, which is 1, plus 1 minus 1 times that width, 0.5, which we know that's going to be 0, so really x0 is just 1. And x1 is 1 plus, now 2, because I is 2, to get that x1, minus 1 times 0.5. Well, we know that's technically just adding a 0.5, and we get 1.5. And as you make all of these by hand, you should see them jump in increments of 0.5. Oh, sorry. I just completely ignored what I was saying. Now, let's do the right endpoint briefly. So start again with I is equal to 1. You're going to get your first point, x1. Well, we know it's going to be a, which is 1, plus I, which is 1, times the width, 0.5, which is 1.5. And if you do this, you will get the same variables that you got over here. The only difference is here, right here, right here. The only difference is that you'll have a different x0 and you'll have a different not x, xn, that last triangle that you end up using. So now we need to plug in all these values. Let's start with the left. If I do f of x0, that's technically me doing f of 1. And that's going to be 2 times 1 squared minus 1. 2 minus 1 is 1. Okay. F of x1 is 1.5. So 2 times 1.5 squared minus 1.5. Okay, I'm just gonna use my phone. Let's see. 2 times 1.5 squared minus 1.5. Okay, so we get a nice 3. Then f of x2 is technically just f of 2. 2 times 2 squared minus 2. That's gonna be that's 8 minus 2, that's 6. Okay. Lastly, f of x3. Hold on. I muted myself, so hopefully y'all didn't hear that. Okay. F of 3. No, sorry, I keep wanting to do 3. 2.5, so it's 2 times 2.5 squared minus 2.5. That's gonna be a 10. Let me see. Okay. Then we would go ahead and figure out the area. So we do 1 times the width, which if they all have the same width, this isn't funny enough, I didn't do this example in the other class, but I'll do it here because even I was like, oh, that's an easy assumption. You go 1 times 0.5 plus 3 times 0.5 plus 6 times 0.5 plus 10 times 0.5. Well, they all have a 0.5 multiplying. So technically you do 0.5, distribute out. 1 plus 3 plus 6 plus 10. It's all equivalent technically, and that's 20. So 0.5 times 20, that's just going to be 10. And if you want, you can just start off this expression and chuck that in your calculator. Look at 0.5 plus 3 times 0.5 plus 3 plus 5, and you do indeed get 10. How about over here? Because at the end of the day, that's the approximation. But what does this guy say? Well, technically speaking, you don't have to do too much more work. You already have f of x1. It's the same thing, right? So you know f of x1 is going to be 3. And f of x2 is going to be 6. And f of x3 is going to be 10. But you don't know what f of x4 is. So that one you do have to figure out, which is asking what f of 3 is. So you got 2 times 3 squared minus 3. That's going to be 18 minus 3, and that's 15. So what is the area approximation here? Well, 0.5 times 3 plus 6 plus 10 plus 15. I'm just going to put that expression to the calculator. And you get 17. This process of approximating the area under a function using rectangles is called the Riemann sums. The more rectangles we use, the better approximation it will be. Imagine an infinite number of rectangles. So the area would be equal to the limit as we do all of these possible rectangles. Now, this problem is called the definite integral. If f of x is a function defined on a to b, the definite integral from a to b is given here, where it's that integral, but we stop at the upper and the lower bounds of our interval provided. Now, granted, there's a couple of trivial things with this, but it's not too crazy. First, we note that this, if we're doing it from a point to a point, that integration part will be 0. Think of the rectangle example. If you're doing just a sliver under the curve, well, that sliver is almost going to be non-existent. It's going to be 0. If you have these bounds, then you should be able to flip those bounds. If you have a constant for the integral, that should be able to come out. If you're adding or subtracting integral, you can distribute the integral. If you have c in between a and b, that typo made it into this thing, then you could technically split the integral of that c. Instead of you go a to b, you go a to b to c, and then you posit c as well. Now, the main definition from the fundamental theorem of calculus, if f of x is continuous on the a to b, and capital F is any antiderivative of f, then we can define the integral as what we see here. So a lot of these properties can be proven knowing this definition. For fun, it's like a little side quest. If you want, you can prove that these are equivalent. If you do the left-hand side, you get f of b minus f of a. If you do this, you get f of c minus f of a plus, if you do this, you get f of b minus f of c. The c's will cancel out, And then you have negative f of a plus f of b, which is the same thing as saying this. Okay, so let's go ahead and do these. So let's go ahead and recall the antiderivative from our review. If we're going backwards or actually really quick, let me go ahead and just rewrite that. X to the power negative 2 plus x to the power of 3 dx. And then I'm going to go ahead and rewrite that as x to the power of negative 2 dx plus integral x to the power of 3 dx. And then from there, I'm going to do the same antiderivative. Let's do x and then negative 2 plus 1. That's going to be negative 1 plus c. From 2 to negative 1. And then plus, same thing here, we got x to, here I'm going to write c1 actually, just so we know that those are two different constants. To 3 plus 1, which is 4, over 3 plus 1, which is 4, plus c2. To negative 1. Then from here, we're going to plug in, like we do, b and a into this antiderivative function. Or, actually, let me take a b and fix that so it's a bit prettier. We got negative 1 over x plus c1. And then this I don't really have to fix. Okay, so let's plug that in. We got 2, negative 1 half, plus c1, and then minus when's a. So minus negative, or no, sorry, minus 1 over negative 1. And then minus c1. Write this, I think I accidentally did double negative. Let me go ahead and write this a bit more proper. I put the negative there as well. Okay. And then I'll copy this guy here. And I feel like I need to color code a little bit. I have all these colors. Let's go over here. That's gonna be plus parentheses for 2. So we got 2 to the power of 4 over 4 plus c1, or c2, excuse me. Then minus this but negative. So negative 1 to the power of 4 over 4 plus c2. Okay, so it looks messy, but still, we can definitely get it down to be something more palatable. From here, we should see, it's a plus, we should see that the c's will cancel out. And then we can have negative 1 half. We have a double, triple negative, so it's going to be minus 1. Let me just double check that. Negative, and then negative, yeah, okay. And then we, let's put that in the set of parentheses. And plus 2 to the power of 4, which is 16 divided by 4, so 4. And then minus 1, because that's it's going to come out to 1 over 4. So we definitely need to simplify that. Let's go ahead and just rearrange this to be 3. Combine those two, and then combine these to be negative 3 over 4. So just 2.25. And that's going to be our answer. Now, keep in mind a couple of things. Sometimes you want to distribute, sometimes you don't have to. I make the choice most of the time of not distributing, only when I really need to make sure to separate it. But remember, you can only separate it when it's adding or subtracting. 1. 2. Notice how useless including the c's were. And the property says any antiderivative. Why does it say any antiderivative? Well, because technically c, no matter which way you write it, will always cancel out. So you're better off not including the plus c at this point anymore. All right, let's go ahead and do this one. I'm going to go ahead and distribute. And then let's do the here. Let's just do it all in one color. We got, let me see. So that's going to be 3 over, or 3 times x to the power of 1/2 plus 1, so 3 over 2, divided by 3 over 2. And this time I'm going to include the plus c. I'm going to go from 4 to 1. And then minus, you could have factored out the 2 here as well, technically. X to the power of 4 and then 1. Or not to the power, starting from 4 and ending at 1. Here we could definitely polish it up. Those 3's factor out, and then dividing by a fraction, we can just rewrite that as 2x to the power of 3 over 2, 4, 1, minus 2, x 4, 1. I could go an extra step. It's a bit annoying, but I could definitely go an extra step and just factor out the 2's. You don't have to do this, but I'm going to do this. And then right here, we should stop. Because even though you could maybe factor out the x, that would definitely be a little more informal than factoring out the 2's, because 2 is a constant. X, we technically don't know what it is, so we might as well just plug it in. So I have 2 parentheses, and then let's start here. For this, I do want to color code just a bit. We have, I'm just going to rewrite this as square root of 4 to the power of 3 minus square root of 1 to the power of 3. Oh, wait. And then for this one, I have minus parentheses 4 minus 1. Oh, okay. This one wasn't that crazy looking. Well, 4 square rooted is 2, and then 2 to the power of 3 is 8. And then 1 square root is 1, 1 to the power of 3 is 1. And then 8 minus 1 is just 7. And 4 minus 1 is just 3. So we have 2 parentheses 7 minus 3, which is just 4. 4 times 2 is 8. And that's going to be your answer. Now, granted, you didn't have to factor out the 2's as much as I did. But there's not necessarily a way around it. It's just the way it is. What you also could have done is if you left this all together, you could have done just one bracket, but I leave that up to you. Or actually, let me show you what I mean. So if you left this all together, you technically could have done it as 2x to the power 3 over 2 minus 2x from here, and then you would get 4 for this, which is just 2 times 8 minus 2 times 4. And then that would be minusing this whole product, which is just 2 minus 2. Let me put that in parentheses. Well, we know that's 0, so that's going to just go all the way to 0. And then over here we have 2 minus 8, 2 minus 4, 16 minus 8. Well, that's just 8. So you could have done that as well, but that's, I'm just going through like every step possible. Okay, let's wrap this up. We're almost done with this. We have this here. We know that's just ln. So we're doing ln of x for 2 and 1. Technically, we can, put this into ln of 2 minus ln of 1. And then ln of 1, just it's a little late as I'm recording this, so I don't know why I feel the urge to double check. Ln of 1 is indeed 0. So that's going to come out to 0. So you can technically simplify this to ln of 2. And over here we have the opposite, or not the opposite. The step before cosine is sine. So sine of x from pi over 2 to 0. And that's sine of pi over 2 minus sine of 0. That's definitely 0, and that's going to be 1. And the answer is 1 minus 0 is 1. Okay. That's going to wrap up today's video, guys. There's going to be no worksheet for today because I'm giving you 2 homeworks, and the review packet wasn't dense. It's literally only 3 pages, but I'm giving you guys the space. So if you need to review stuff, you can go through the YouTube channel that I have all my Cal 1 videos. I haven't organized them yet, but you can scroll through those and see what's what. Or if you just have any questions on like, hey, I didn't get this, just let me know, okay? But I'm treating 1 as a space to do the review, okay? All right. Let me know if you guys have any questions, and we're gonna continue this tomorrow. So see you all then. Bye bye.